Okay. Hello, everyone. Welcome to the 19th of our talks in the AI Age Institute seminar series. Today, it's my pleasure to welcome Arnab Ghosh, who is going to give us a talk on model-free RL for constrained MDP, foundations and applications. Arnab is a research scientist at the Ohio State University in the Electrical and Computer Engineering Department, and he is directly affiliated with the AI Age Institute as well. So without further ado, I'll give the floor to Arnab and we'll ask questions towards the end of his talk.
Yeah, thanks, Ailem. I mean, you can also ask questions in between talk. Yeah, right. Yeah, as Ailem mentioned, so I'm going to talk about model-free RL for constraint MDP and welcome everyone. Okay? Thanks for your time. So first, I'm going to briefly talk about the motivation. So we are living in the world where you are seeing the boom of devices, right? So you have like devices are also getting connected, devices are taking decision. And probably in the near future, not very far, you also have the vehicles are talking to each other, vehicles talking to base station. And we are talking about smart city where you have smart grid, smart transportation, smart mobility, smart manufacturing, everything is getting smarter. So in this kind of system or interconnected system, which I describe as a complex system, is very important how to take decisions. So here devices may individually or collaboratively take decisions, but the underlying question is that how to or learn to take optimal decisions. So this is what I'm interested in. Now, if you see this decision making in terms of complex systems, so you will identify some common theme. For example, consider the autonomous vehicle. Like it wants to reach the destination at minimum amount of time, but also wants to maintain safety, right? Avoid collisions. I'm talking about robot, it wants to reach the goal state, but in the minimum number of steps while avoiding obstacles. You can think of optimize the energy consumption. We want to minimize the energy consumption while completing important jobs. And it is kind of very basic question in a lot of application in the edge computing, for example, data center, sensor network, cloud computing. So as I mentioned, there is a common theme. All wants to maximize their objective or minimize their cost, but need to satisfy some constraint. And it is not related to these kind of examples. You can find a lot of examples. For example, resource allocation. You want to maximize the throughput of different traffic subject to delay. And even in different other applications. For example, you can talk about, okay, I want to find a policy while ensuring fairness across the users. I want to build my portfolio while maintaining wealth above a certain threshold, even in the finance. And so this brings the question how to learn to take decisions which will maximize objective while satisfying the constraint. And you will see that, okay, in most of this application, you can cast as constraint Markov decision process. So you have some kind of underlying decision process. You can take this kind of structure and you can cast as some kind of CMDP or constraint Markov decision process. So this is what I'm going to talk about, okay, so how to learn in this kind of constraint Markov decision process. So in this aspect, I have made contribution in both in the foundational front as well as the application front. For foundational, I propose the provably efficient model-free constraint RL algorithm with linear function approximation. That means for large state space. And I am fortunate to collaborate with Xingyu from Wayne State University. I think he's here, and Nesh Shroff. Also, the first paper that has been accepted in New Dips, it is for kind of episodic setup. We also extended to the infinite horizon setup in the ICLR version. And we also extended to the non-stationary CMDP. So if your MDP is kind of changing. So in this regard, I'm fortunate to work with Hong Hao and Lei Ying from University of Michigan. And we also have achieving some kind of hard constraint violation and regret. So that is I'm also going to talk about what do you mean by constraint violation and regret in a few minutes. And not only in the foundational front, we also make contribution in the application front. For example, beam selection using kernelized bandits under interference constraint. Okay, so in this regard, I am collaborating with Yuntian Deng and Abhishek Gupta, and it was the runner-up for the Best Student Paper Award in the recent YOF. And we also, as I mentioned, this kind of application, we not only simulated in kind of toolbox, in MATLAB toolbox, we also experimented on data set, which is obtained from the Northeastern University. In fact, we are right now collaborating with Northeastern University for phase control for intelligent reflecting surfaces. So this is kind of ongoing work. And also in the adaptive bitrate selection for video streaming. Okay, so we also use the constraint RL algorithm for video streaming. Again, this kind of ongoing work I am doing with Xin Yu. I think she's also here from University of Minnesota, Zili Zhang, and Xin Liu from UC Davis. We are experimenting again on the 5G data. So see, if you, in this application, we're also trying to see, okay, in real life, how these constraint RL algorithms will work. And not only this ongoing work, I've also made some contribution in the past. For example, RL-based traffic light controllers. If I have time, probably I will show some nice video like what we have done there with when I was at Imperial College of London. And when I was a postdoc at Purdue University, we also talk about deep reinforcement learning-based vehicle dispatch. Again, we experimented on the real data set there. Okay, so this brings to the first part of my talk, which is the foundational part. Okay, the foundational model for model-free RL for constraint MDP. Okay, so as I mentioned, like a lot of decision-making process can be cast as CMDP. So what is a CMDP? So in the CMDP, what you have with the, okay, at certain step H, you are having some policy, you're taking action corresponding to some policy. What the policy means is that it is a probability with which you take an action H at state XH, okay? So you take an action, you get a reward and you get a utility, okay? So if you are having some trouble, what is the utility? You can think of also as cost or negative of the cost, okay? Now you get a reward and probably get utility or cost, take it on the chin and move on to the next state. So next state is sample from this probability distribution. And here we are talking about large scale system. For example, the state space can be infinite. The state cardinality can be infinite, but we are restricting the action space to be finite throughout this talk. And here in this example, what I show is that, okay, you have some kind of hard stop after capital H steps, but you can, I will show like how can you extend it to the infinite horizon case as well. Okay, so now what is the objective here in this CMDP? So you have the value function for rewards. You are accumulating reward from steps 1 to capital H, and you're also accumulating utility from steps 1 to H. And what do you want to solve? Solve this optimization problem. You want to maximize the expected cumulative reward, but subject to the constraint that expected cumulative utility is kind of greater than equals to some threshold, okay? So you can also consider add up to the multiple constraints, or if you're thinking of cost, this expected cumulative cost is less than equals to some threshold. Yeah, so this is also possible. Okay, so now if as I told, okay, a lot of applications you can cast as some kind of CMDP problem, but if you're not believing me, so now I'm give you some example, okay, how can you cast it? So for example, like you have some kind of safe intelligent controller, which one always wants to be in the safe regime, right? So now if you're taking action, your dynamics is changing, but I want that, okay, I always want to be in the safe regime. Now you can think of, okay, this is a CMDP where your threshold is kind of H, right? You will forcing that, okay, always I will get the utility of 1. When I'm in the safe state, I will get the utility of 1. I always want to be in the safe state. And you can think of this problem can be some kind of network controller whose job is to maintain a Q state below a certain threshold. If it is below a certain threshold, I will get a utility, right? And another example you can talk of, okay, for example, job scheduling, where the jobs arrive in sequence, like you want to schedule the jobs to reduce the delay, but you also incur some cost on the electricity consumption. So I will revisit this example, but you can also do some mental exercise to cast in the CMDP framework. Okay, but what we want here is that, okay, I know nothing about the system, right? I want to learn some good policies, okay? So what do you mean by learn some good policies or employ some good policies here? So at each episode, I am fixing my policy, I'm taking some actions from this policy, okay? And I do that over these capital K episodes. Now, what I want is that I want the total reward is close to the optimal one in an episode while almost satisfying the constraint, because I know nothing about the system. So it is apparent that, okay, probably initially I will violate the constraint, but I want that, okay, I will almost satisfying the constraint, or this overall constraint violation will be small over this capital K episode. And we have the bandit feedback. We only observe the reward utility for the actions taken over an episode. I do not observe the rest. Okay, and again, based on the received data, probably I will play a different policy at the next episode, and so on. And this is where the exploration versus exploitation trade-off comes, whether I should stick to the current policy or should we explore. But here also need to ensure that, okay, I am not violating the constraints. So there is some additional challenge. Okay, so now what we want is that we want to minimize this regret and the violation. So what is the regret here? So it is the difference from the optimal value function. Obviously, I do not know the optimal value function. So that's why it's known as the optimal policy in hindsight, or you can think of some genie has given me this optimal value. And this violation is easy to interpret. So like if you have Vj1 pi kx1 is greater than equals to b, I am not violating the constraint, otherwise I'm violating, so I'm adding this penalty. So this leaves the question, right? So can we design an algorithm to choose policies that can simultaneously guarantee an optimal upper bound on regret and violation? So this is the provable efficient guarantees, right? So I do not want only some kind of guarantee on the regret. I also want some kind of guarantee on the violation. This is what it differs from the unconstrained case. Okay, so now there has been some approaches to solve this or to find this provable efficient guarantee. The most straightforward way is the model based. You can estimate the transition probability, estimate the model, but obviously it is computation intensive for large state space. So remember, we are talking about infinite space cardinality. Also, there is another approach is model free, which is more popular and is very easy to implement. But finding theoretical provable bound is more difficult, right? So if you see that, okay, there are some approaches for model free, for example, policy gradient, but they rely on some kind of simulator. So a simulator you can think of is an oracle which provides the next state. So if you inquire any kind of state action pair, it will give you the next state, the reward, utility, all you want. So it's a kind of exploitation balance is kind of easier here, right? Because you are not rolling out the trajectory. And also these results are not a high probability bound. And its bound is worse compared to the model-based approaches in terms of age. Okay. But there is also other approaches without simulator. For example, primal dual Q learning. Now, if you see the result here, okay, so this regret bound depends on the cardinality of the state space, right? So that means that, okay, if you have infinite cardinality, this result does not make any sense, right? And here, even the regret bound is not optimal in K, right? Even for tabular case. For example, for model based, the regret bound is K to the power 0.5. And if you see here, it is K to the power 0.8. So that brings the question, can we develop a model free, obviously without simulator, provably efficient constraint RL algorithm for large state space and for infinite state space? And the answer is yes, we can do that, at least for linear CMDP. And this is the first such result. And it has some nice properties. Even we can ensure that, okay, we can guarantee zero violation. So we do not need any kind of simulator. This is model free. So computational complexity is much smaller. And it is order optimal in K, right? So that is why we bridge the gap between the provable performance guarantee and the computational complexity. We obtain the order optimal K result even using the model free approach for the large state space. Okay. So this is our contribution. Okay, so now if you are wondering what is kind of linear CMDP, so we have some kind of linear structure in the transition probability. So if you have known feature space phi, and here the transition probability is linear in this feature space, and the reward and utility also linear. Even though you know phi, you do not know this mu and theta. So there is still some degree of freedom. And if you are wondering about some examples, so any kind of finite state action space or tabular case, you can cast as a linear CMDP. So these results also hold for tabular case. And it's shown in some kind of recent empirical study that for the unconstrained case, even if you assume there is kind of linear CMDP and use your algorithm, right? Oftentimes you show some kind of excellent performance for the empirical data set, right? So that means that there is some kind of load and dynamics. If you know the good feature space, there is some kind of load and dynamics in the most of the experimental data set. So this is the result for our case. So if you see that regret and the violation, both are order of square root k. And it does not depend on the cardinality. It only depends on the dimension of the feature space D, but it does not depend on the cardinality of the state space. So we break the curse of dimensionality. And if you're wondering how it works compared to the lower bound, so we are nearly optimal in K. We have some kind of log factor, right? But other than that, we are nearly order optimal in K. Okay, still, can we get a better bound? It still remains open, and more importantly, we match the result on the model-based result in H and K if you're talking about some kind of small state space or some kind of tabular case. Okay, and it also gives some other implications. So as I mentioned, we can achieve a zero violation with still square root of K regret, but with slight worse dependence on H. So we are adding some kind of extra H factor, but we can get zero violation there. And it also gives a sample complexity bound. So what is the sample complexity bound? So if someone asks you, okay, can you give me some kind of epsilon optimal policy, which is feasible, right? So that means that if you run this policy, your value function or reward value function will be epsilon close to the optimal value function, but it will be feasible. And I give the number, okay? This is the number of samples that you need to obtain the result. Okay, and our algorithm guides on how to obtain such a policy. It is also some kind of optimal sample complexity result in, at least in epsilon. Okay, so this is the implication of a result, and now I'm going into the algorithm. What is the algorithm behind it? Okay. So in this kind of algorithm, we use the structure of the linear CMDP. As I mentioned, okay, this is kind of this here we are considering linear constraint Markov decision process, and in this case, you can show that okay, your Q function is indeed linear in the feature space. So you can search for such a kind of linear parameters, right? And now if you talk about unconstrained case, we have this dynamic programming approach, which is already been shown, okay? Even if you do not know the MDP, right, you can have a dynamic programming approach. So basically solve a linear regression to estimate parameters, and then you can take action greedily with respect to this estimated Q function. And that will solve. But even in the constraint case, this dynamic programming approach does not work. Even if you know this MDP, right? So because you need to solve a linear programming with state action occupancy measure as variable, right? Now that means that if you have a large state space, your linear programming problem will explode, because you have to solve infinite dimensional LP. And more importantly, you do not know the true MDP. This is fine if you know the true MDP, but even if you do not know the true MDP, how to find it? So what we do is that we adapt the LSBIUC with the unconstrained version in the primal dual type. So we take the Lagrangian and put it in the objective with some scaled dual variable, and then we solve the min-max problem. Okay. So now the strong duality holds if you have a strictly feasible policy. That is the Slater's condition. Even though the original problem is non-convex, the strong duality holds if your Slater's condition is satisfied, which is used for our analysis purpose. Okay. Now, what is the algorithm ideas? I will give you some kind of high-level idea what we are doing here. So think of this, okay, this is the feasible space, and we are creating an envelope. So this envelope contains the feasible space with high probability. So the idea is that as you gather more data, we are shrinking this feasible space, okay, and hopefully it will converge to the original feasible space. Okay, now what the primal dual algorithm does is that, okay, suppose okay, you're taking an action in the rate space. That means it is outside of this envelope. So then I will increase the dual variable so that I force to take action, probably episode next to that, in the envelope, within this envelope. Then the question is how to build this envelope, how to shrink this envelope, how to build this envelope, and how to learn the reward value function. It's not about only the feasible space. You also need to learn the reward value function, right? Okay, so this is what we use the linear structure. Again, we solve the linear regression problem, right, to find this parameter by fitting the Q function in the Bellman's equation. And then you add some kind of bonus term. So this is from the unconstant version, like you add some kind of bonus term to maintain an overestimation or maintain this envelope. Because the only thing you need to do is that, okay, finding this value function, right? How can you find a value function? And that is what you need, value function estimation. And that is what you need this policy. What will be the policy there? Now, naturally, the try will be, okay, we are doing some kind of unconstrained version because we are doing this Lagrangian. So why not try the greedy one? So try the greedy one with respect to this composite Q value, right? But it will not work. But why it will not work? Because it is not Lipschitz. So if you see in the right-hand side, right, you have two reaction space, right? You have, okay, now your Q function, if you change your Q function, your optimal action will change, because if you're doing this greedy policy, even though the sum of these value functions are the same, right? But your individual value function differs. I mean, here it is 1, and if you're taking some different action, it is 10, right? So that means that you are not learning in a meaningful way both this reward value function and the feasible space, okay? You cannot learn using this greedy policy. So that means that you need some kind of much more smoother policy, and that is why softmax, we are using the softmax with some particular temperature coefficient, which is essential to get this provable efficient bound. Okay. So our algorithm is like this: we estimating the parameter, we having this policy with respect to the softmax, and then we update the dual variable depending on how we were doing in the dual space, whether we are in the estimated value function is satisfying the constraint or not. And the final result we obtain by having this dual variable learning rate. Okay, so but as we mentioned, okay, we can also achieve zero violation while maintaining the square root of k regrets. The idea is that instead of b, we will use b plus epsilon. So that means that we are solving some kind of epsilon tighter optimization problem. So you can think of, we are fooling the agent, believing that, okay, probably your feasible space is much tighter, and probably you also need to shrink your envelope a little bit more. But if you're shrinking your envelope too much, probably your regret would degrade because you are not learning in the reward space, right? You are not exploring in the reward space. So that means this kind of epsilon, which is order of 1 over square root k, that is what you need. Okay. And now we see some kind of toy simulation results. Again, I'm talking about the job scheduling setup, that example that I give. So initially what you have is that your job stack is full. You have the complete job and your state space from 0 to 9. So 9 means, okay, your job stack is full. You want to decrease your job stack and your horizon length is 10. Now, if you can schedule or not. And if you're scheduling, you can reduce your job space or you can reduce your state space by at most 2, but you have some kind of time dependent reward, or here time dependent cost, okay, because of the energy cost, which might be time dependent. But you also get a utility. If you're reducing the state space, you are getting an utility, okay? So what do I want is that at the end of this episode, right, I want that, okay, at most 2 jobs can be present. This kind of arbitrary number. The idea is that, okay, I will try to schedule when the cost is small. So this is the idea. Now, if you see the result, right, if you have this epsilon equals to 0, right, these violation scales at most square root of k, right? But as I mentioned, you can also play around this epsilon. You can shrink your envelope, like believing that, okay, you have this kind of solving some kind of tighter optimization problem. Then you can see this violation indeed goes to 0. Obviously, the average reward will be kind of smaller, right, when you have higher epsilon. Okay, but that is expected. So now, as I mentioned, that, okay, not only in this kind of episodic setup, we can also talk about without episode or infinite horizon setup. So suppose you have some kind of continuously learning, right? The agents are continuously taking decisions. For example, in the job scheduler is not ending with at the certain episode, you are continuously warned that, okay, the Q state will be below a certain threshold, right? So in this case, you talk about average reward. You are averaging over all the rewards over this time horizon capital T, and also in the average utility. And we talk about maximize this average reward subject to the constraint that your average utility is greater than equals to some threshold. Okay, so now I'm not going into the details, But the idea is that if you see that you can employ this episodic setup algorithm and you can get sublinear regret. Okay. So the idea is that, okay, you can have this T length horizon and you can divide into episodes with episode length H, right? And you can employ the policy that you have shown. Now, the only thing is that you need to somehow be careful about this episode length, because if you are choosing too small H, probably they will be much more transient. You are not close to the steady state and probably will not learn in a meaningful way. But on the other hand, if you choose high value of H, probably you are not capturing you are not changing your policy to, I mean, you are waiting too long to change your policy, right? But you can also have some kind of more complicated algorithm to get square root T regret, and you can also use the ergodic structure if the MDP is ergodic, right? For kind of not very complicated algorithm, but I'm not going into the details there. So instead, what I'm going to show you some kind of probably more interesting, what is kind of deployment efficient learning. Okay. So what is the motivation here is that, so right now what we have some kind of upper bound of this violation term, right? B minus BJ1. Now you can see that there is some problem. So suppose you have some kind of series of policies for which when the episode length is odd, you are feasible, but when the episode is even, right, you are infeasible, right? But you can somehow negate these two. You can if you're summing over, right, you can get a 0 total violation. But you can see, okay, but even the number of episodes where infeasible policies are employed can be large, right? So what we want is that even when we are learning, right, when we are taking decisions in the online learning, we want to employ policies which will be close to optimal, but only be infeasible sublinear number of times, right? As the episodes grows, right, it will only be sublinear. It will only grow sublinearly. So that means that, okay, the ratio of episodes where the infeasible policies are deployed and the number of episodes goes to 0 as k increases, right? Or k goes to the infinity. Right? But this kind of violation, or which we call as soft violation metric, will not work. So what we need some kind of new metric, which is the hard violation, right? So here, even if you're feasible, we are not adding negativity, right? If you're feasible, we are adding 0. If you are infeasible, obviously you are adding a positive penalty, right? So this is the hard violation. Now we show that, okay, if our algorithm which we proposed achieves this kind of square root k regret and square root k hard violation. Okay, and here we are not assuming some kind of strict feasibility, so square root k is also the best possible hard violation bound, right? And again, this algorithm is kind of model free, and again, this kind of first such result for model free algorithm, even there is no such result for the small or kind of tabular case. This is the first such algorithm for model free case. And it matches the model-based result, right, for the LP formulation or linear programming formulation for tabular case. And remember that linear programming formulation is not possible for infinite state space because you have to solve infinite dimensional linear programming. And this is the first result that, okay, you can still achieve square root k regret and square root k hard violation using this primal dual adaptation, right? Now, if you see, okay, what is the high level idea behind this algorithm? So what we do previously, right, when you're talking about soft violation, so if you have kind of taking an action which is in this red region, we are increasing the dual variable, right? So that, okay, eventually I will take actions in this envelope, within this envelope, right? But what we are doing here right now, we are forcing that at every episode, we are not waiting for the next episode. We are forcing that, okay, at every episode, you have to take action within this envelope. Your policy should be like, okay, it has to be within this envelope. And how do we do that? We find some kind of right dual variable match within each episode, okay? But I'm not going to the details, but this is the high level idea, what we are doing here, how we are achieving this kind of hard constant violation bound. Okay, and again, if you see the simulation result, right? So now this current approach, which is specific to this hard violation, it gets square root of k at most. It scales at most square root of k in our approach, right? But obviously we have kind of losing in terms of reward, right? Even though the earlier approach that we have for the soft violation, even the hard violation metric is kind of scaling sublinearly, but it's not as at the square root of k. It is kind of larger, right? But obviously we are getting some kind of higher reward, right, in the earlier approach. Okay, but again, if you remember that there is another term, there another parameter that we can play around, for example, this epsilon, right? So now if you observe that, okay, you can choose some kind of higher epsilon, right? And you can probably get some kind of similar kind of effect. So your average reward is kind of same, and your hard violation bound is also of the same order, right? Even though this kind of epsilon, okay, which is only meant for example, reducing the soft violation towards zero, it's still kind of achieving some kind of similar result. So that means there might be some kind of underpinning or some kind of relationship between these two. But the bottom line is that the algorithm that we provided here, it has a theoretical guarantee, right? And we do not need to calibrate or tune this epsilon. Right? Okay, so this leads to the last part of, this is the summary, the last slide of this part one. So what we learned is that CMDP captures many practical decision-making problems, right? And we provide the first model-free RL algorithm which achieves optimal regret and zero violation. And in the process, we bettered the model-free tabular case result as well. Okay. And we show that greedy policy on this composite Q function does not work. So instead, we need to work on the softmax policy. And I want to point out that it also has some kind of larger underpinning. For example, learning in the so if you have multiple objectives when you're trying to learn in this kind of a large state space. So it shows that, okay, the actor critic algorithm, for example, the actor critic deep deterministic policy gradient, which also tries to find some kind of greedy action, is also there is some kind of convergence issues, and softmax solves that. So it has some kind of larger underpinning, not in this kind of constraint Markov decision process. Okay. And we show that, okay, it is possible to achieve optimal regret and hard violation bound, even we can achieve result sublinear regret for the infinite horizon setup. So that leads to the end of this part one. And if you have any question, I can make some time for questions at this moment. Okay, so if there is no questions, I will continue for the second part. So this is the applications part. And the first application I'm going to talk about is the beam alignment for time varying channel via kernelized bandwidth. And the first I talk about, okay, the motivation behind it. Now you need to align the receiver and transmitter antenna, because any kind of misalignment reduces the throughput significantly, right? If we have, and obviously the choice can be exhaustive search. You sweep across all directions, right? But it will have some kind of higher overhead, and if the channel is time varying, probably it will lead to some kind of degradation in performance. Like whatever you have obtained, probably it is no more optimal. You can also try to find, okay, why not try to model the channel gain and try to find the optimal direction? But here the signals reach the receiver using multiple paths. So some kind of modeling this channel gain is also kind of difficult here. And the third challenge is kind of interference. You also want to ensure that the interference at the neighboring terminals is kind of bounded. What we want to do is that, okay, can we learn to decide the optimal beam alignment configuration using past data, right? In the process, we want to handle the challenges. For example, non-stationarity, if the channel is varying too much over time, and want to learn to satisfy the interference constraint. And we also want to learn in a provably efficient manner. So I'm going to talk about it a little bit later. So the idea is that minimize the dynamic regret and again, some kind of violation bound. Okay. And what we do is the online learning. So the idea is that you maximize the received signal strength. Here X is the beam vector, and subject to the constraint that, okay, the interference constraint, that means the received signal strength at the neighboring terminals is less than equals to some threshold. And if you notice that here we are having some kind of time dependent function in ft and gt. Okay, and again, this is a bandit feedback. We only, if you select x, you only get a noisy version of ftx and gtx. Now, as I mentioned, okay, received signal strengths are some kind of nonlinear, non-convex functions of beam direction. So how to learn those? Okay, so we seek to learn functions in the reproducing kernel Hilbert space. Why we are choosing that? Okay, here take a moment and pause a little bit and take a step back. So here, I mean, in terms of beam selection, you already cast as a multi-arm bandit problem. But what we want to achieve is that RKHS is much more enriched. Okay, and we can model the correlation across beam directions. So for example, if the beam angles are somewhat close, probably we can also expect that, okay, the received signal strength will also be kind of close, right? But it also difficult to get theoretical bound, right? And we also want to handle the interference constraint and time varyingness. Okay, so what we want to achieve here is that, okay, to minimize the dynamic regret and violations. If you see here, the optimal solution varies with time. It's no longer constant. So if you, that's why you have fkxk star, and this is the beam direction that you are choosing, this fkxk, right? This is the dynamic regret and violation. Okay, if you are violating the constraint, that means that if your gkxk is greater than some b, right, you are violating the constraint. You have accumulating the violations here. And this brings the question, can we learn to take actions with sublinear dynamic regret and violation? Okay, and the answer is yes, we can, at least for bounded functions in this Hilbert space. And the idea is that, again, using the primal dual algorithm. So to think of that bandit problem is also some kind of RL problem, episodic RL problem, where the step length h is kind of 1. Okay, and we give the new algorithm, that is a primal dual restart Gaussian process UCB algorithm.
So can I just ask a quick clarification question here?
Yeah.
Previous slide. So are you assuming that this GK of xk minus b, that this quantity can never be negative? Is that the assumption?
No, it can be negative. Yeah. So again, you can have some kind of a negative, I mean, the kind of feasibility, and it can negate the positive violation. Yeah, it can be negative. We are not minimizing the hard constant violation here yet. Yeah.
I see. So basically, you can make up for any violation by keeping it as a
right. Yeah.
So from a physical meaning perspective, so if I remember this correctly, GK is the individual violations, that it's that the whatever the other nearby nodes are receiving. Is that correct?
Right. Yeah, we are considering only one node, yeah, but you can extend it to the multiple nodes as well. Yeah.
So what is it that you're trying to sort of associated with then the GK? Maybe I'm not very clear about that part.
Oh, so GK is that, okay. So here, okay, so let now, yeah. So GK it is the interference. So it is the received signal strength at the neighboring receivers. Okay, you are trying to, and this is what we want. Yeah.
I see, but so I'm not quite sure how this GT or GK minus B being negative might mean. That's the part that
I mean, you can mean that, okay, so what I want that, okay, the received signal strength at the neighboring terminal must be less than equals to B, but it might be less than B, right? It might be B minus 1 or B minus some. It is kind of value, right? I want that, okay, this is kind of less than equals to some value, so that this signal to noise ratio will be in this zone, which is still okay to the neighboring terminal. Okay, so that means that, okay, if you have GTX which is B minus 1, it's kind of fine. So that means GTX minus B is negative 1, you can think of, right?
I see. Okay, so I don't want to just stop this, but maybe we can take this discussion later on and continue that. Thank you.
Right. Yeah. So now now we talk about the algorithm idea. So we have this we have this feasible space, and if you remember, we are creating this envelope, right? Now, if your feasible space can also vary with time. So now if you had to have this envelope, right, which is covering all this feasible space, where you do not know where the feasible space is like. So that means that you are not learning in a meaningful way because your envelope becoming too large. So what we do is that, okay, if your envelope becomes too large, I will cut it and restart the learning process, okay? And how do you, when do we cut it, how do you cut it? Okay, so this is, we use some kind of algorithm for that in our YF paper, but we have done it in a more sophisticated way and extended to the RL version in our AI stats paper. Okay, and how to construct that envelope, again we use the Gaussian process bandit. So it is a nice property of if you have, if you are in functions in the RKHS, you can learn using this Gaussian process bandit, right? Now, as I mentioned, the idea is to have some kind of meaningful application kind of guarantee. Now, if you use this kind of, we have used first a simulation result using the MATLAB toolbox, and we inject some kind of abrupt change at iteration number 100 and 300, right? So now if you have this, okay, so we have two versions of our algorithm. So one is the no budget and is the budget. So budget version means that we are using some kind of estimate, okay, how far the change can be. Suppose there someone gives you some kind of estimate of that. But in the no budget, we are not using any estimate. So we can also be fine if you do not have this estimate. So if you see in this kind of, when you're injecting this change at the 100, obviously the regret increases. And this GPUCB is the no restart version. We are not restarting it, right? So now if you are 100, okay, there is some kind of change, and this green curve, to recognize it, restarts the learning, right? And even in the 300, okay, again, there is some kind of change. The regret increases a little bit. It sees that, okay, and again, it restarts and it decreases, okay? And even in the violation part, right? So if you see the violation, it decreases towards 0, okay? But okay, so this is shows that, okay, why the restart kind of works in this case. And now, as I mentioned, okay, how does it perform on the practical data set? That is that we are collaborating with the Northeastern University, and we show this result on the eFlash data set. So this data set is already there, and so it is not kind of exactly in the online learning format. So we have some kind of data on the received signal strength indicator for certain directions. Okay, and here we have these two vehicles. Okay, one is the intending vehicle, and the second vehicle, that is where you want that, okay, interference to be somewhat, received signal strength should be somewhat less than equals to some kind of threshold. And if you see the result there, right, we see, okay, we still see the regret and violation decreases in our approach. I mean, compared to the no restart version. And if you remember, the first idea was that utilizing some kind of correlation across the beam directions, right? So this is the result if you increase your sigma. That means that if you have some kind of higher correlation, so if you see the regret is kind of decreasing more, even though the violation performance kind of same. But if you increase too large, the performance again degrades, okay? So that means there is some kind of sweet spot. I mean, there is some kind of value of, there is some kind of correlation, but not much correlation that you can explore. Okay. So what we show is that we cast the beam selection problem as a constraint bandit problem, and we use the Gaussian process bandit to learn the function in the RKHS. And we propose a primal dual restart adaptation to handle non-stationarity interference. And we also obtain sublinear dynamic regret and violation, but we do not show the bound there. Okay, what is the bound? But you can see it in our paper. And our algorithm indeed reduces the regret and violation on both simulated and real data. And we are also on with the ongoing work for controlling. So this is some kind of online learning based control. So here our algorithm will guide, okay, what should be the phase direction, for example, for intelligent reflecting surfaces. So this kind of ongoing work. So I'm going to talk about some other application, okay? So it is kind of adaptive video streaming. So now what is the adaptive bitrate algorithm? So you can see the chunk of a video, which is some kind of sub part of a video. So video can be 4 minutes long, and each chunk can be 4 seconds long. The idea of adaptive bitrate algorithm is that, okay, I want to stream my video at high quality, right? That means that I want to download at a higher bit rate that will increase the quality of experience. Right? but it may lead to buffering, because if your bandwidth is limited, it may take longer time and you will see some kind of buffering at your screen. The idea is that, okay, I want to maximize this bit rate, but also minimize the stall time. And you can cast as a multi-objective RL. This is the well-known algorithm Pensieve, which already does that. And they have this kind of multi-objective. One is the reward and the weighted penalty. And this is the best known performance so far on the 4G data set. It selects what should be the bit rate. Okay. But if you see the performance in the 5G, right? So it is the experiment done at the University of Minnesota, 5G data set, which has high variability, so high throughput with low throughput in between, high bit rate and a lot of stall. Okay, so we want to be in this extreme right-hand corner, right? In the extreme right-hand upper corner. But if you see in the Pensieve, there is a lot of stall time, even though if you get a high bit rate. On the other hand, this kind of robust MPC is kind of doing good. I mean, at least you are in this box, upper end box, but your bit rate is barely there. So if your bit rate is kind of close to the 80%. So what we want is that, can we achieve better bit rate than the robust MPC and smaller stall time than Pensieve? Okay, can we get some kind of best of both the world? Okay. And that's why we use this model-free constraint RL. Okay, and we experimented on 5G data trace. I think Shinju might correct me. This time becomes 76 training tests, and we use the 45 testing. We use the primal dual actor critic method, and if you see the result, right, this is where we are. So we are getting a better result compared to the robust MPC, right? If you compare it in terms of mean bit rate, and we are getting a better stall time. I mean, lower stall time compared to Pensieve. Even the stall time is smaller compared to the robust MPC. At least the mean stall time, not the 95%. So that what do you mean is that, okay, if you see this curve, we are right there. We are right in this right hand side upper hand corner, right? We are in this box, and we are doing better in terms of bit rate, at least in the robust MPC. But still, this is not the end of the world. We are still trying to do something. Okay, for example, we are leveraging on different types of constraint. Probably cumulative constraint might not be a good one. We might see some kind of other constraint for getting more generalizability. We are doing some testing on the generalizability factor here. So I'm not going to the details. If you're interested, we can discuss it later. So instead, what we do, we're going to do some kind of future work. So what is so in the future work, I can see you kind of foundational questions as well as some kind of application front. So foundational question for constraint RL. So what we have shown is the CMDP setup is that what you take an action at a given state, right? And you get a reward and utility, right? But you probably that might not be a good model. I mean, in some practical setup, you only get some kind of feedback at the end of the trajectory. You can see some kind of human which is giving you the feedback. You only know, okay, whether it is some kind of good one or bad one, right? How can you learn there? And suppose you cannot change your policy frequently, how to learn efficiently there? And suppose if you have some kind of offline setup where no further data is coming by, for example, in many applications, the data is there already, and you cannot increase your data set. So then what is the best you can do? As I mentioned, we are already trying to do some kind of theoretical understanding of different types of constraints, learning again in the nonlinear function approximation domain. So apart from this foundational question, you can also see some kind of applications question as well. So for example, as I mentioned, we are already doing some kind of control these intelligent reflecting surfaces. And we are trying to see, okay, for edge devices, important, like how to take low computational complexity decision where latency is kind of factor. And how can you generalize decision? For example, if you are training some data, training your algorithm for a given set of network, right? How can you adapt to the different set of network? I mean, meta learning kind of thing can be useful here. And also it has a more application for other domains as well. And also what I'm going to work, I'm also working with Purdue University, for example, with Elena and Tulane University. So here we are talking about intelligent decision or control, or kind of robust RL policy, where we are trying to protect against state information perturbation. So if you see that, okay, you have this true vehicle state, but someone perturbs your state space and give you some kind of little bit wrong state, right? Now you take a wrong actions, you take a left turn, then you will be headed to the collision, right? You want to avoid it, you want to protect against it. And then we need to understand, okay, which MDP structure is more robust to this kind of attack. Probably we want to formulate some kind of game theoretic application. So suppose the adversary is trying to give you some kind of perturbation, what is the equilibrium there? Okay, how can we take action there? So it can also have some kind of other implications or other domains, for example, robust fair decision making and misspecification error. So that is brings to my end of this talk, and I am happy to take questions or some kind of discussion that you want.
Hi, Arnav. Yeah, I have 2 questions. Great informing talk. So the 2 questions are from the first part. So can you provide an intuition on why can you achieve the state cardinality-free sample complexity?
Sorry, can you repeat your question?
Yeah, so I believe your regret analysis is independent of the state cardinality, right? Compared to previous results. Can you give an intuition or like explanation, any kind of technique that you used to achieve this better result?
Right. Okay, got it. Okay, but if you see the result, right? So it depends on this cardinality of the feature space, right? So it depends on how enriched your feature space is, right? So if your feature space dimension is high, right, obviously your regret bound will also be high. So now what we are doing is that, okay, even if you have infinite state space, we are like some kind of probably multiple states are somewhat captured in a single point there in this feature space, right? So this is what we are using in this kind of linear CMDP, some kind of structure that we are having in the linear MDP model.
I see. Oh, yeah. So just to be clear, which one is D is the dimension of the feature space?
Yeah, D is the dimension of the feature space.
Oh, okay. Thanks. Right. A second question is, you mentioned you also did the work on average reward case. Is it for a general MDP or also for a linear MDP?
It is for linear MDP, yeah. Linear
okay.
MDP. Yeah.
Okay, thanks. Yeah, that'll be all my question. Thank you.
Yeah.
Any other questions? Maybe then I can just, continue my question.
Right.
This GT business. I understand the reason you're using this function. So, but when you look at the optimization problem formation on page 42.
Yeah, okay.
Pages that. Yeah, for the violation here can also take on negative numbers. So in other words, you can actually make up for the violations that has been by performing better, right? Is that the idea?
Yeah, I mean, you can. I mean, so the total violation does not mean that, okay, here, okay, you are not violating the interference constant. So just let me show you. Yeah, but again, as I mentioned here, right? So if you see the RL, where we can also type this optimization problem, we can add some kind of epsilon there, right? And we can force this kind of hard violation, that probably the better metric there again. Which will be lead to some kind of square root K or some kind of much better kind of performance in terms of violation. If you want that, you can type these optimization problems to kind of fool that agent that probably you are solving some kind of tighter optimization problem, what it has been. Because you know that we are trying to have some kind of envelope, we are trying to explore in this space, right? Yeah. So that is also possible, but we have not done this experiment yet. But I suppose that, okay, if you do that, probably you need to see much more violation degradation. Yeah.
I see. So I mean, okay. So I understand all the theoretical reasons why you may want to keep it this way.
Yeah.
But I'm also trying to reconcile it with the practical implications of what.
Right. Yeah. So even if you see this violation, it's kind of going to zero. Obviously, it is the, yeah. So we have not plotted the hard violation here. Yeah. So I take my word back. Yeah.
Okay. Right. Thank you. Any other questions? Well, if not, then let's thank the speaker once again, Arnab. Thank you very much for this great presentation. And
thank you.
Thanks everyone for attending today's talk. Look forward to your attendance as well next week. Have a nice day.
Sure. Yeah. Thank you.